Okay, so in this next question we're asked to find the volume of the solid obtained by rotating the region bounded by the given curves about the specified line, and then to sketch the region, the solid, and a typical disk or washer. So the equations we're given are y equals x third, and y equals x cubed, and it's going to be bounded by y equals x, and x has to be greater than or equal to 0, and we're going to be rotating this about the x-axis. So if we go over to the graph over here, we can see that we have a graph, and I've only got it set up for these 5 pegs on the x-axis and these 4 pegs on the y-axis, because x has to be greater than or equal to 0. So we know we're not going to be graphing into the negative space here. And the reason I've got 4 pegs here is because I'm scaling the x's and y's both by 0.25. So it goes 0.25, 0.5, 0.75, 1. And this 5th one wasn't supposed to be there, it just is. And then this is 0.25, 0.5, 0.75, and 1. So if we're doing y equals x at x equals 1, y would also equal 1. So it'd be like that. And then at x equals 0, y would also equal 0. So we'd have just this straight slope going like that. And then for y equals x cubed, 0 cubed is 0, and then 1 cubed is 1. So it'd be like that. We'd just have another dot there. So when we draw the x cubed graph, though, it's important that we draw it a certain way, because as we know, the x cubed graph goes like this, and it's going to curve up and continue on like that, basically. It wouldn't go straight up like that, it would still curve, but you get the idea. And so we can see that we're going to be finding the volume of this region right here, this kind of half circle region, and we're going to be rotating it about the x-axis, meaning that this line is going to become like this, so that it's at 1, negative 1, and then this line is going to go like this. The x cubed line is going to go like this. Like that. So that's what it looks like when it's rotated about the x-axis. Now let's take this point at 0.75 here, right here. Let's just make a dot at 0.75. If we draw the solid of revolution, we have it going like this. We have a circle like that. And then, but we need to watch out for this other point at 0.75. There are 2 points at 0.75. So there's this point right here, and that's going to go like that. And then we draw a circle. And now we should be able to see that this looks like a washer right here. We have a disc with a hole in the middle. So we actually have a washer here. So when we go to integrate it, we're going to be, when we go to do the integral to find the volume, we're going to be using the washer method. So when I do the integral, I'm going to be integrating along the x-axis, and I'm going to be integrating from 0 to 1, because that's where the 2 curves meet, and I'm going to be integrating from pi times the outer radius, which I'll denote as r sub o squared, minus pi times the inner radius, which I'll denote as r sub I squared. So now the challenge is going to be figuring out what our inner and outer radius is. So we go back to the graph here. The outer radius, this outer ring, is given by y equals x, so our r sub o is going to be x, and our r sub I over here, you can see in the inner radius that our inner radius is given by the x cubed curve. So our inner radius is going to be x cubed. So now I can rewrite this as volume equals the integral from 0 to 1 of pi times x squared minus pi times x cubed squared. And now you can actually just pull the pi's out of this and put it in front of the integral, because pi is a constant, so that's what I'm going to do. So I'm going to have pi times the integral from 0 to 1 of x squared minus x cubed. Squared is the same thing as x to the 6th, because whenever you raise a power to another power, you just multiply those two powers. So it's going to be x to the 6th, like this. And then when I go to actually evaluate the integral, I'm going to have pi times 1/3 x cubed minus 1/7 x to the 7th. And if you're wondering why that is, you can just take the derivative of these. You would drop down the 3, and 3 divided by 3 would be 1, and then 3 minus 1 up top would be 2, giving you x squared. And the same thing for x to the 7th. You just drop down the 7, these would simplify to 1, and then 7 minus 1 is 6. And we're going to be evaluating that from 0 to 1. So when I go to write this, I'm not going to write the 0 part because it would just be 0 minus 0. So I'm just going to write 1/3 minus 1/7. Because 1 cubed is 1, and 1 cubed times 1 is 1 cubed, and 1 raised to the 7th is 1, and 1/7 times 1 is 1/7. So now I'm going to multiply 1 cubed by 7 on the numerator and the denominator, and I'm going to multiply 1/7 by 3 in the numerator and the denominator to get them to have like denominators. So I'm going to have 7/21 minus 3/21, and then I'm going to rewrite this up here. That's going to be 4 pi over 21, and that would be my answer. That would be your volume. Okay, so in this next problem we're asked to do the exact same thing, except our equations now are y squared equals x, x equals 2y, and they want us to rotate it about the y-axis. So let's head on over to the graph here and let's graph this out. So let's graph out x equals 2y first. So if we go ahead and divide by 2 on both sides, we'll see that this is the same thing as y equals 1/2 x, meaning it at x equals 0, y equals 0. And then it would just have a slope of 1/2, meaning we go up 1 over 2, up 1 over 2, and then up 1 over 2 like this. And then we can even go down 1 to the left 2, down 1 to the left 2, and then down 1 into the left 2 like that. And then I can go ahead and draw my rough line going through there. And now for y squared equals x, we can go ahead and make a table of values here. So I have x and I have y, and I'm going to go ahead and plug in values for y because that's easier, because I won't have to take the square root that way. So at y equals 0, x equals 0. At y equals 1, x equals 1. So we just go up 1 over 1. And then at y equals 2, x would equal 4. So we go 1, 2, 3, 4, and then 1, 2 like this. And then at y equals 3, x would equal 9. This doesn't go up to 9 though. But we can see that our shaded region is this little crescent piece right here, because the two curves intersect at 0, 0 and at 4, 2. And they wanted us to rotate it about the y-axis, meaning I'm just going to reflect these points over the y-axis. So for example, this point up here, 2, 4, is going to be negative 4, 2. So it's going to go 1, 2, 3, 4, and then up 2, like that. And then this point here, which was 1, 1, is going to be negative 1, 1. So it's like that. So then our curve, this is what our y squared equals x curve looks like when it's rotated about the y-axis. Then for our 1/2 x equals y curve, I can just do the same thing, except it would be, instead of going up 1 to the right 2, it would be going up 1 to the left 2. So we go up 1 to the left 2, and then up 1 to the left 2, which is just there, and then we draw a curve like that. And we can see now that we've rotated it about the y-axis. And if we pick this 1, 1 point here, and we start tracing what it would look like to be rotated, we rotate it like that, we see that it's making a circle like that. But then we also have this point over here. This point is where x equals 2, so 1/2 times 2 is just 1. So it's at the same y value as this one, and we can see that if we draw a circle around that, well, it looks like we have a washer shape. So we're going to be using the washer method to integrate this, and we're going to be integrating with respect to y, meaning we're going to be integrating on the interval 0 to 2, because the y value where they intersect is 2. So when I go to write the equation, I'm going to write v equals the integral from 0 to 2 of pi times the outer radius squared minus pi times the inner radius squared. And I'm just going to write dy just to reinforce the idea that we're integrating with respect to y. Now I'm going to factor out the pi and put it in front of the integral just to get that step out of the way. So I have pi times the integral from 0 to 2. And then when I look at the outer radius, this is the outer radius here. You can see that it's the 1/2 x equals y line right there. But because we're writing it, we're doing this with respect to y, I'm just going to keep it as 2y. So I'm going to write 2y squared minus, and then the inner radius is given by the y squared equals x curve. So I'm going to write y squared squared dy. So then I can simplify this into pi times the integral from 0 to 2 of 4y squared minus y to the 4th dy. And then when I go to evaluate this integral, I'm going to have pi times y cubed, and then there's going to be a 4/3 in front of it. So 4/3 y cubed minus 1/5 y to the 5th, like that. I'm going to be evaluating from 0 to 2. Again, I'm not going to write the 0 part out because it would just be 0 minus 0, which is 0, and it wouldn't affect the answer or anything at all. So I'm just going to skip going over the 0 step. If you want to do the 0 step, feel free to, if it helps you understand it better. If you need to do the 0 step, go ahead, but I'm going to skip it. So I'm just going to have pi times 4/3 times 2 cubed minus 1/5 2 to the 5th. And then when I go to evaluate this, it's going to be 4/3 times 8. 4/3 times 8, like that, minus 1/5 times 32. And then I'm going to bring it up here, and I'm going to write pi times 32/3 minus 32/5. And so I'm going to multiply the 32/3 by 5 in the numerator and the denominator, and I'm going to multiply 32/5 by 30 in the numerator and the denominator to get them to like denominators. And then what that is going to give me ultimately is 64 pi over 15. So if you were to get them to like denominators and then subtract them, your final answer would be 64 pi over 15. Okay, so in this next question we're once again asked to find the volume of the solid obtained by rotating the region bounded by the given curves about the specified line, and then we're asked to sketch the region, sketch the solid, and a typical disk or washer. So the two graphs we're given, or the two curves we're given that are going to make the solid are y equals x squared and x equals y squared, and we're going to be rotating that about y equals 1. So if we go to the graph over here, I've got it graphed out and I've got y equals 1 mapped out. Now if we take a look at this right here, we've got a standard parabola y equals x squared, so we can just go ahead and graph that so we know that it's going to be at 0, 0, 1, 1, and then negative 1, 1 as well. And we get a curve that looks like this. So that's y equals x squared. And then when we go to do x equals y squared, it's going to be the same thing, just turned on its side basically. So where a normal parabola looks like this, x equals y squared is going to look like this. So that's what we're going to graph. So again, we're going to have 0, 0, and then 1, 1, but then we're going to have 1, negative 1, like this. And then we go to graph it like that, and we see that we have our parabola. And if we continued, we'd see that it goes like this, and y equals x squared goes like that, like a normal parabola. Hold on. Yeah, okay. So like that, and then like this. So we can see that the region we're going to be graphing is this little teardrop shape right here. And they want us to rotate it about y equals 1, which means we basically, this point is on y equals 1, so it can't be rotated any further or any more than that, but this point is not on y equals 1. So we're going to go like that. And then so our x squared curve that was like that is going to be now like that. And our y squared curve that was like that is now going to look like this. So this is what it looks like rotated. It looks kind of like wings of some sort. Now this is going to be hard to do because the shape is a little bit small, but if we take this point here, for example, and we demonstrate the rotation, we see it goes like that. But there's also this point right here, and when we demonstrate the rotation of that, we can see that it forms a washer shape. So we're going to be using the washer shape to integrate this, which means we're going to do the volume equals the integral from 0 to 1, because it goes from 0 to 1, 0 to 1 of pi times the outer radius squared minus pi times the inner radius squared. Now the radius is going to be a little bit tricky because we have to take into account that we rotated it about y equals 1. So because of that, it's going to be 1 minus whatever these equations are, 1 minus x squared, if you will. So this inner radius right here, this one was given by y squared, x equals y squared, if you remember. So we have x equals y squared, but we're going to be integrating it with respect to x. So let's just start by finding the outer radius first. So when we look at the outer radius, we have to take into account this y equals 1 that we rotated around. And we know that the outer radius is this thing right here, and we know that this was given by the curve y equals x squared. So because of this line y equals 1, our outer radius is going to be 1 minus x squared. And we are going to be integrating it with respect to x, by the way. So it's 1 minus x squared. Now our inner radius is this thing right here, and that's given by our x equals y squared. But in order to get that in terms of y, because in order to get it in terms of x, because right now this is kind of written not in terms of x, it's written in terms of y, we're going to take the square root and we're going to say y equals the square root of x. And the reason it's the positive, I'm not even going to get into that. So our inner radius is going to be 1 minus root x. And now we can solve this integral. And again, I'm just going to factor out a pi in front of the whole thing. So it's going to be pi times the integral from 0 to 1 of 1 minus x squared minus, I'm going to have to write this a little bit lower. I'm just going to block this off for now. Minus 1 minus square root of x squared. Now when we go to do this, 1 minus x squared squared is going to be 1 minus 2x squared plus x to the fourth. And this 1 minus square root of x squared is going to be 1 minus 2 root x plus x. Which means we're going to get pi times the integral from 0 to 1 of 1 minus 2x squared plus x to the fourth. And then I can go ahead and distribute this minus sign to all the terms here. So I get minus 1 plus 2 root x minus x. So this 1 and negative 1 cancel out, and we're left with pi times the integral from 0 to 1 of x, of negative 2x squared plus x to the fourth plus 2 root x minus x. And now we can go ahead and evaluate this integral. I'm going to erase all this work up here, so just make sure you have it written down. Alright, so now I'm going to drag this up here like this, and so when we evaluate this integral, it's going to be pi times negative 2x squared is going to be x cubed negative 2/3, like that, negative 2/3 x cubed plus 1/5 x to the fifth, plus the thing to remember here is that the square root is the same thing as raising something to the 1/2. So if we were to undo the integral, it would be x to the 3/2 and then we want to make sure that when we bring this down, whatever will be left will be 2. So I can say 4/3 like this, and then if I do 4/3 times 3/2, I will be left with just 2. So 2, and then 3/2 minus 2/2 would be 1/2, and you'd get the square root back. So that's why it's that. And then this would be minus 1/2 x squared. And this would be from 0 to 1. And then when we go to do this integral, I'm going to skip the 0 step because it would just be 0, the whole term would be 0. So what we have is pi times negative 2/3 plus 1/5 plus 4/3 minus 1/2. Now, a number that these all share in common, a number that the denominators all share in common is 30. So if I do that, I'm going to get so we multiply negative 2 by 10, so we get negative 20 over 30 plus 6 over 30 plus 40 over 30 plus 15 over 30, or minus 15 over 30. Minus 15 over 30. So then if we evaluate this, we'd get pi times 40 minus 20 is 20, so we get 20 over 30 plus 6 over 30 minus 15 over 30. And then 20 minus 15 over 30 would be 5 over 30 plus 6 over 30. Sorry, I'm writing this incredibly messy. 5 over 30 plus 6 over 30. And we bring down that pi to be multiplied by whatever the sum of these two is. And that gives us 11 pi over 30. And that would be my answer for that one. Okay, so in this next question we're asked to find the volume of the solid obtained by rotating the region bounded by the given curves about the specified line. And then we are asked to sketch the region, the solid, and a typical disk or washer. So the equations that we're given that are going to make up the region are y equals 1 plus secant of x, and then y equals 3. And they're going to be rotated about y equals 1. So let's go ahead over to the graph here. And as you can see, I've got the dotted line right here showing y equals 1, which is where we're going to be rotating our region. And now all we need to do is just find our region. So if we go ahead and graph the y equals 3 line first, it's going to just be a simple straight line at y equals 3. And that's going to be our y equals 3 line. Now the important thing to remember is that secant of x is the same thing as 1 over cosine of x. So 1 plus secant of x is the same thing as 1 plus 1 over cosine of x. And if we go ahead and graph this out, what we're going to find is that these y equals 3 and y equals 1 plus secant of x are going to intersect at pi over 3, comma 3, which is up here, and pi over 3 is 3.14 divided by 3. 3.14 and then a lot of other digits divided by 3, but it's basically going to be just over 1. And so we can say that that's 1 point there. And because the secant graph looks like a parabola, it will be will have another point at negative pi over 3, comma 3. So that will be negative just over 1, comma 3, like that. And then if we plug in 0 for x right here, it would be 1 plus cosine of 0, which is 1 plus 1, which is 2. And then so we would connect it here, and you can see that we'd have this parabola looking thing like this. And then if we were to move to the left or to the right any further, we would eventually encounter an asymptote, where if we did something like y equals pi over 2 or 3 pi over 2, we would get an asymptote. So, but we're not going to do that. It just wants us to do this region right here. And so this is the region we're going to be rotating about y equals 1. So when I rotate it about y equals 1, I'm just going to, for example, this bottom point here, the vertex of this parabola, is 1 space away from y equals 1. So I'm going to move it down 1 space, and then I'm going to move it down another space to rotate it. And I'm going to do the same thing with pi over 3 and pi over 3 comma 3 and negative pi over 3 comma 3. So these are 1, 2 spaces down from y equals 1, so I'm going to move them 1, 2 spaces like that. And I'm going to do the same thing and with pi over 3 comma 3, and then this is going to be our rotated region. And then we can rotate y equals 3 down, and it would just look like a straight line like this. And now we can see that this is our rotated region. Now when we go to draw the solid of revolution that's made by rotating it, we're going to see something interesting. So if we draw it like this, and then we make this curve right here, but then we also have to remember that there's a second point up here and down here as well. And then so if we draw it like that, if we rotate this second point, we can see more clearly now that what we're dealing with is a washer. So we're going to be using the washer method, and we're going to be integrating with respect to x. So this is going to be volume equals the integral from negative pi over 3 to pi over 3. And the reason that is because the shape exists, the solid exists from negative pi over 3 to pi over 3. So those are going to be our bounds of integration, and then it's going to be pi times the outer radius squared minus pi times the inner radius squared. Let me make that I a little bit more clear that it's an I. Okay, so now we want to find our inner and outer radius. So if we go back to the graph here, our outer radius is this, and it's given by the curve y equals 3, but we're rotating it around y equals 1. So we're going to do 3 minus 1, which is 2. So our outer radius is 2. Then our inner radius is given by the curve y equals 1 plus secant of x. And since we're rotating it about y equals 1, we're going to be subtracting 1. So we're going to have we're going to have 1 plus secant of x minus 1, which is just going to be secant of x. And then so I can go ahead and factor out a pi over here. So I'm going to have pi times the integral, and then negative pi over 3 is the same thing as 5 pi over 3. And if you're wondering why that is, it's because it's a circle, so you can move counterclockwise and clockwise. And if we were to do negative pi over 3 plus 2 pi, which is 6 pi over 3, if we get them into like denominators, then you have 5 pi over 3. And the reason I'm adding 2 pi is because I'm saying, okay, I want this negative pi over 3 to be something that's a positive radian value that I can more readily identify off the top of my head. And so I'm just going to move it one rotation around the unit circle, basically, is what you're doing there. So we have pi times the integral from 5 pi over 3 to pi over 3 of 2 squared minus secant of x squared, and this is dx as well. We're integrating with respect to x. And then so when I go ahead and evaluate this, I'm going to get pi times the integral from 5 pi over 3 to pi over 3 of 4 minus secant squared of x. Secant squared of x dx. Now, in order to integrate this, you're going to need to know your trig integrals. And in order to know your trig integrals, especially with secant squared of x, it would help to know your trig derivatives. So we know that the derivative of tangent of x is secant squared of x. So if we're going backwards, the integral of secant squared of x is just going to be tangent of x. So I'm going to have pi, when I evaluate this, I'm going to have pi times the integral of 5 pi over 3 to pi over 3 of, I meant to evaluate the integral, not rewrite it. So it's going to be pi times 4x minus tangent of x. And this is going to be from pi over 3 to 5 pi over 3. So I'm going to erase this work that's written up top here, so make sure you have it written down. So I'm going to bring this up here now, and I'm going to get pi times 4 times pi over 3, 4 times pi over 3 minus tangent of pi over 3, uh, 4 times pi over 3 minus tangent of pi over 3, and then that's going to be minus 4 times negative pi over 3. And the reason I'm writing it in negative pi over 3 instead of 5 pi over 3 is it's going to help us simplify later on down the road, and it's also just the same thing as 5 pi over 3. So I'm going to have 4 times negative pi over 3 minus, and then when I do it for tangent though, you can write it whichever way you want for tangent. I just like to write it as 5 pi over 3 because I can think about what the answer is more easily than negative pi over 3. But if you can see it easier with negative pi over 3 instead of 5 pi over 3, you can go ahead and do that as well. So like that, and then I'm going to enclose these in square brackets just to emphasize that this pi is going to be multiplied to whatever answer is left. So I'm going to have pi times 4 pi over 3, 4 pi over 3. Tangent of pi over 3, if you don't know your unit circle values, I would suggest that you memorize your unit circle values by now. But if you don't have them off the top of your head, you can look at a reference image and you could see that the coordinates for tangent of pi over 3 would be 1/2 comma root 3 over 2. And because tangent is sine over cosine, it would be root 3 over 2 over 1/2. And you could simplify the 2's, you can cancel them out. So tangent of pi over 3 is just root 3. So we have 4 pi over 3 minus root 3 minus negative 4 pi over 3, negative 4 pi over 3 minus, and then tangent of 5 pi over 3 would be the exact same as tangent of pi over 3, but there would be a negative for the y value, because if you think about it, 5 pi over 3 is the same thing as 300 degrees, so your y value would be negative, so your coordinate would be 1/2 negative root 3 over 2. So when we go to do tangent of 5 pi over 3 and it's sine over cosine, it would be negative root 3 over 2 over 1/2, and you could cancel out the 2's to get negative root 3. So tangent of 5 pi over 3 is negative root 3, and we're going to have a minus a negative, which is the same thing as addition. So it's going to look something like that. And then we're going to have pi times 4 pi over 3 minus root 3 plus 4 pi over 3, because we're now distributing this negative 1 to both terms. So negative 1 times negative 4 pi over 3 is 4 pi over 3, and then negative 1 times root 3 is negative root 3, like this. So now what we have is some simplification that we can do, and I'm just going to erase this bottom bit right here. So when we go to solve this, we're going to have pi and then times 4 pi over 3 plus 4 pi over 3 is 8 pi over 3. 8 pi over 3 minus 2 root 3. And we can actually factor out a 2 from this whole thing. So that will give us 2 pi times 4 pi over 3 minus root 3. And these two are equivalent, because if we just multiplied the 2 to both of these terms, we'd get pi times 8 pi over 3 minus 2 root 3. So that would be my answer for that one.